Góðan daginn, velkomin á Málstofu Hafrannsóknastofnunar. Í dag erum við með frábæran gest frá Færeyjum, Bogi Hansen. Switch to English now. Bogi Hansen is a physical oceanographer at the Marine Research Institute in the Faroes. He did his master's studies in theoretical physics at the State University of New York at Stony Brook, and then a PhD in physical oceanography at the University of Copenhagen. His main research focus is on regional oceanography in the Northeast Atlantic and on the Faroe shelf, looking among other things on the North Atlantic thermohaline circulation and the physical effects on primary production and ecosystems, i.e. linking the ocean with our climate and biology. He mentioned, not to me, but to another person in the room a few minutes ago, he is one of those great guys who should be retired, but he isn't, so, which is good for us. Today he will be talking about the flows of the warm and cold water masses across the Iceland-Faroe Ridge. Bogi.
Fyrirgefðu, ég verið að tala ensku. Yeah. The flows across the Iceland-Faroe Ridge. Just to be sure that we agree on the geography, here are the Faroes. The Iceland-Faroe Ridge is this submarine ridge between me and you, and it's part of the Greenland-Scotland Ridge system. Now, I've been wondering what, I don't want to insult you people by telling everybody what they know before, but I thought that this would perhaps be a bit broad and very varying, or variable, no, not variable, community. Anyway, so I thought I'd start by giving a fairly broad introduction to the topic. And starting with the flows across the Greenland-Scotland Ridge as a whole. If we start in the surface, we have the warm inflow west of Iceland. We have the warm inflow between Iceland and Faroes. And we have a warm inflow between the Faroes and the European continent. These bring heat into the Arctic, keeping large areas free of sea ice and giving us who live in them a very, very nice climate, I feel at least. This is what we call the Atlantic inflow. Of course, when you have a continuous inflow of water, water must flow out as well. A bit of that comes in the surface in the East Greenland current or through the Canadian archipelago on the other side of Greenland. But by far most of the Atlantic inflow is converted into what we call overflow water. By cooling, atmospheric cooling, the water becomes much denser, sinks to large depths, fills up the basin north of the Greenland-Scotland Ridge, and then pushes its way through the deep passages in this submarine ridge system. There is an overflow through the Denmark Strait, just west of here. There is another one through the Faroe Bank Channel, which is actually the deepest channel across this ridge. A weak flow across the Wyville-Thomson Ridge, and then an overflow across the Iceland-Faroe Ridge as well. Many people also here in Iceland have been working on trying to quantify these flows. How much water is flowing in these currents? And recently there was a paper by Svein Østerhus et al., many al, collecting observational estimates. If you take the Icelandic flow, it's a bit less than 1 square drop. 1 Sverdrup is 1 million cubic meters per second, approximately the same amount of water as is flowing in all the rivers of the world. The flow between Iceland and Faroes is about 4 times as strong, and then there is a flow between Faroes and the continent. If you go to the overflows, the strongest one is the one through the Denmark Strait, then comes the one through the Faroe Bank Channel, weak one across the Weibel-Thompson Ridge, and then something that I'll return to, the overflow across the Iceland-Faroe Ridge, which we don't really know how large it is. So why do we have these flows? There's not only one answer to that, but the main reason, at least as I understand the system, is this. Again, you have the Greenland-Scotland Ridge here, Greenland, Iceland, Faroes, Scotland. If we imagine taking a section, a vertical section, across the Greenland-Scotland Ridge, it looks something like this section that you see in the slide. As I said, up in the Arctic Mediterranean, north of the ridge, the air cools the water so that it becomes very dense, sinks to large depths, fills up the basin, very cold, sub-0 degree water, fills up the basin well above sea level, and so you have a continuous overflow. This is very important for many reasons, one of them being that while it's up north, it absorbs carbon dioxide from the atmosphere and then brings it along, carrying it into the deep parts of the ocean where carbon dioxide actually should be in the natural climate system, and so ameliorating the effects of global warming. But for our purposes, if you have a continuous removal of water by the overflow, if nothing else happened, then the sea surface up north would simply lower all the time. But as soon as the water in the surface realizes that there's a slope on the sea surface, it starts to flow downwards. So my main point here is that the main mechanism driving both the overflow and the Atlantic inflows is the atmosphere cooling the surface water. As I said, it's not the only mechanism, but as far as I can see, it counts for about 2/3 of the inflow. Which of course means that with global warming, you expect less cooling. You expect more fresh water from Siberian rivers, from melting Greenland ice sheet. And so perhaps the pump could weaken. This has been, I can say, feared for a long time. And as you may know, in the last IPCC report, they conclude that the Atlantic Meridional Overturning Circulation, or AMOC as it's called, is very likely to weaken over this century. And this is a very fundamental part of the AMOC. But there is another aspect to this, and that is the fact that all this dense water in north of the ridge, it's like a giant dam. And even if you did not replenish this dense water, it would still take decades to drain it out, which means that the overflow, and therefore also the Atlantic inflow, should be expected to be very stable. And just to confirm that that is actually the case, we in the Faroes have been monitoring the overflow through the Faroe Bank Channel almost 3 decades now. And this is how it looks. The thin lines are monthly averaged volume transport, millions cubic meters per second. The thick line is annual average. And you see it's around 2 million cubic meters per second, 2 Sverdrup, but very, very stable. Okay, that was background. Now let us try to get a bit closer to the Iceland-Faroe Ridge, starting with looking at how does the water, the warm surface water, how does it get to the ridge? And this figure shows drifters, surface track drifters that have a drogue at 15-meter depth, so they're not very much affected by wind. And the panel to the left shows all the drifters that passed north of the Faroes. And you see all of them passed through the Iceland Basin. And even some of those that flowed south of the Faroes also came from the Iceland Basin. And that is also what we, the message that we get from what we oceanographers call the mean dynamic topography. That's just a fancy word to say average sea level. This is a rather confusing figure, but the white lines are the bottom topography. The thick white line is the 1,000-meter contour. So here you have the Iceland Basin, there you have the Rockall Hatton Plateau. And then the black lines are isolines for how high the average sea level is. And first you see that there's approximately almost half a meter difference between the Norwegian basin and the coastal waters of Scotland. But across the Iceland Basin you have about 10 centimeter tilt due to the Coriolis force. And according to theory, these lines that you see should represent streamlines, showing us how the water flows. Now, I've made some lines dashed. Let's make them red. This actually should show all the water in the surface that crosses across the Iceland-Faroe Ridge. And again, you see it comes from the Iceland Basin. Of course, for this to be, you have to rely on the mean dynamic topography, and there are many uncertainties in that. But a recent publication by Koman et al. From the Iceland Basin supported this picture, I find at least. So this is sort of the flow system you get for the water passing towards the Iceland-Faroe Ridge in the surface. And if you want to monitor it, and we've wanted to do that for a long time, the smart thing to do is to monitor it where it's narrowest. And we did that. So we chose this monitoring section going right north from the Faroes. If you look at this section, we started CTD, I think, very much inspired by the Icelandic standard stations, which had started well before that. We started our own standard stations, and this was one of them. And we've been having regular CTD cruises along this monitoring section 3 to 5 times a year. The figure shows the average salinity from CTD work. So the high salinity wedge that you see here, that's the Atlantic water, and separated from the Arctic waters that have much lower salinity. If you looked at the average section of the average temperature, it would look very much similar. But if you want to know how much water flows, you need also to measure velocities, and we've been doing that. We have used acoustic Doppler current profilers. which can provide a vertical profile of velocity. We've been using them in the top of traditional moorings, but then they have to be moored so deep that the trawlers don't catch them. So for those locations, we have used ADCPs in these trawl-proof moorings. Monsters, expensive, but we usually get them back with the data. Combining all these observations with satellite data, we have found that, and that's our most recent paper, at least for this region, we find very good correspondence between in situ observations and satellite observations. And by using a very large set of in situ observations, we could calibrate the altimetry data so that we actually now can produce time series of volume transport all the way back to 1st of January 1993, when the satellites started. So the upper curve here shows volume transport. The lower curve shows heat transport relative to 0 degrees. Again, the thin lines are monthly averages, thick lines are annual averages, and again, very, very stable. Certainly not weakening. If you have heard that the AMOC is weakening, this component of the AMOC is not weakening, or has not been doing that for the last 3 decades. Actually, there's been a small, very small, but still statistically significant increase, both in volume transport and heat transport. But let's look a bit closer on the ridge itself. So this shows the bottom topography. The white line is the 500-meter contour. And you see that its ridge is deepest close to the Faroes. In the northern end, there is a series of banks, including Rosengarten. And then you have the western valley as the deep channel separating the Rosengarten from the Icelandic slope. We, in cooperation with many people, mainly in the first years, Detlev Kvartfassel and Svein Österhus, have been deploying these acoustic Doppler current profilers, ADCPs, in troll-protected frames on the, as you see, these locations on the ridge, and now in later years, especially in cooperation also with the Danish Met Office. So we have covered most of the ridge with these ADCPs, which produced velocity profiles every 20 minutes, not all the way to the surface, but quite close to it in most cases, plus bottom temperature. And so what do we learn? If we look at temperatures over the ridge, observations over more than a century have shown that over most of the ridge, the surface layer is dominated by Atlantic water. So the front between the Atlantic water and the Arctic waters is usually east of the ridge, although there are eddies and meanders that may come onto the ridge, certainly. But that is only in the surface or near the surface. When we go deeper, the front comes closer to the ridge. This can be illustrated by a section here across the ridge, which was made by Jens Meinke quite a few years ago. This shows isotherms. Let us enhance the 5-degree isotherm. You see at the surface, it's at the Iceland-Faroe front, but as we go deeper, the front goes onto the ridge, and actually you see that the very bottom water on the ridge is not Atlantic anymore. It is Arctic to some extent. Yeah, now I maybe went a little too fast. This was the plot that Jens made all these years ago. But this is not just one occasion or one location. If you take from our ACP moorings, most of them have lasted almost a year. You see that in all of these, the average bottom temperature is much colder than the Atlantic water. You might perhaps expect that the deepest part of the ridge, close to the Faroes, would be coldest, but that's not the case. The coldest bottom water we see in the Western Valley, close to you guys. So, summarizing, in the surface you find Atlantic water over most of the ridge, but the bottom is dominated by modified Arctic water. So the question is, does this water overflow the ridge? Is there Iceland-Faroe overflow? Actually, it was shown already in the 19th century by Martin Knudsen, who incidentally also was the first General Secretary of ICES. Indeed, there was. But how persistent is it? How large is it? Is there persistent overflow across the IFR, Iceland-Faroe Ridge? Yeah. Yes, there is. And the reason I can say that with a fair degree of certainty is that it's because of one ADCP mooring, which Detlef Kvattfassel, in cooperation with us, deployed, which showed a very persistent and very strong flow close to the bottom at 600-meter depth on the Icelandic slope. This shows the average velocity profile, averaged over 2 years. And in the core, which was just some 50 meters above the bottom, the average velocity was more than half a meter per second. And if you took weekly averages, there was not 1 week with velocity less than 30 centimeters per second. And actually, Perkins et al. Had some shorter moorings close to this location and had a similar conclusion already in 1998. So yes, there is persistent overflow across the Iceland-Faroe Ridge, but where does it cross? So we find it here at Detlef's mooring, but where does it cross the ridge? That was one reason that we deployed these ADCPs already in around 2003, but it was not close to the Faroes, where the ridge is deepest. There is some overflow there, but it's not persistent. And we found also that it's not persistent in the Western Valley, which is close to the upstream region where the water comes from. But over the shallower, more central parts of the ridge, there, these arrows that I showed there, these are the average velocities at close to the bottom. So there you have flow going in the direction of the overflow, and they apparently feed the overflow that Detlef Kvartfassel saw on the Icelandic slope. These measurements are quite recent. The last ADCP was recovered this summer, and they've not been published yet, but Karin Larsen, she is about to publish it. And our colleagues from the Danish Met Office are working on modeling not only the overflow, but other flows across the ridge with high resolution modeling. But why does, if there is persistent overflow, why does it not come over the deepest part or through the Western Valley where it's closest? And I think we found the reason by our experiment that we did, that in these locations, it's blocked by strong Atlantic inflow. And so let's look at the Atlantic inflow, the upper flows. This is what the mean dynamic topography, that is the average sea level, shows in more detail. Again, remember, these black lines should represent streamlines. So you see a flow, inflow close to Iceland, part of it going towards the southeast, but much of it also going back onto the ridge, where it retroflects and then joins the flow that crosses the ridge closer to Faroes. And then, apparently, a recirculation over the Rosengarten bank. We have been trying to, as I said, one should always take this mean dynamic topography with some caution, but actually when we compare our ACP measurements, I say near surface, it may be 100-meter depth or a bit more in some cases, because the ADCPs don't get the flows closest to the surface. But certainly, if we look at the uppermost flows measured by the ADCPs, they fit perfectly with the mean dynamic topography. So there's a strong inflow close to Iceland. Actually, this at this location over the Western Valley, the average speed was 22 centimeters per second, which is a strong flow. And then there are weaker flows, inflows close to the Faroes, and then backflows over the middle of the ridge. You might conclude from this that most of the Atlantic water crosses in your part of the ridge. And that would be nice for you people. But the problem is that this very strong flow over the Icelandic slope is also very narrow, only about 10, 12 kilometers. And it's fairly shallow. The velocity decreases rapidly as you approach the bottom, whereas my flows on the Faroese part of the ridge, they are not as fast, but they represent a much wider area and do not decrease as rapidly with depth. So in fact, when we go and look at the flow in the near surface layer, this is our conclusion in our recent paper. There are two branches. There's an Icelandic branch, but it's fast, but it's narrow and shallow. And then a much wider Faroese branch, slower, but much wider and deeper. And much of the water from the Icelandic branch retroflects back onto the ridge, and part of it actually circulates over the Rosengarten bank. I think for the biologists here, I don't know how much you know, have seen this before, but this ought to be of interest. And just to emphasize that this recirculation is true, these are some of the drifters that passed very close over the Icelandic slope. You see that many of them turned back onto the ridge, and if you especially note the blue track was one drifter that circled at least 2 times around the Rosengarten bank. So that's real. I am approaching the end, fortunately. The fact that the Atlantic water, as it crosses the ridge, much of it is in near contact with the bottom water and over a long period, and the fact that the tidal currents, I haven't mentioned that, but they are very strong over the Iceland-Faroe Ridge and therefore give much mixing, is probably the reason that we see a large cooling and freshening of the Atlantic water as it crosses the ridge. So what I show here are some upstream measurements at one of your Icelandic standard stations and 2 of our standard stations. This one, unfortunately, we don't have any longer. And what's shown in this figure is over the last, what's that, 93, almost 30 years, the average temperature from 0 down to 500 meter depth, sill depth of the ridge. So the inflow has a temperature somewhere between these average. This is the transport weighted average temperature downstream after the water has gone through, crossed over the ridge. So the water is cooled by at least 1 degree, and if you look at the salinity, it is freshened also at least by 0.1. And you might think, oh, what should that matter? So this is my last real slide. If we take the salinity of the inflowing water before it came to the ridge in 2018, it was 35.15 approximately. After crossing the ridge, it was down to 35.3. And the problem is that this is the water that should be cooled and made sufficiently dense to sink. But the difference between the salinity of the Atlantic water after crossing the ridge and the deep water has been reduced to 1/2 by going across the ridge, which means that the possibility for this water to be made sufficiently dense to sink to large depths has been reduced considerably just by crossing the ridge. And that was it. Sorry for...
Thank you, Bogi. We have time for questions. I have one. So the IPCC concluded that it was likely, is the word they chose. That
Very likely, yes.
Very likely was it, that it would slow down.
Yeah.
Is it incorrect according to what you're showing here? Or?
This was during this century. We have only started this century. So I mean, the basic idea is that since it's cooling by the atmosphere that drives the thermaline circulation, and you expect especially the Arctic air to become much warmer, it will cool less and we'll get more fresh water. The problem in many discussions is that we have this part of the AMOC in our region. There is also a part in the Labrador Sea, which many people, especially modelers, have thought this was the dominant region. But certainly it's quite clear from the observations that it's not. It may be, some people claim that the Western AMOC, the one in the Labrador Sea, has weakened. There's much discussion on that. But this one has not, at least during the last 30 years. But it may do so in the future. And that's, for us who live in the middle of it, would be a catastrophe.
Yeah, definitely. Any other questions? I have more questions. I don't want to... Okay, I have one more. It's nice to see all these recent measurements that you've been doing. I miss a little bit the cooperation with Iceland. Is there something we need to do as well? Are we doing enough?
I miss it very much also.
Yeah. Okay. Good that we agree that. And yep.
Yeah, Angel from the University of Iceland. Thank you very much for the talk. It's really nice to see all your work you've been doing for the years, I think. It's like fantastic. I'm very intrigued by that part. The Atlantic flow is when it's crossing the Iceland-Faroe Ridge towards north. It's in very close contact with the lower limb or the upper limb of the lower part of the other machine of the AMOC. And that is a little bit of a sweet spot, because we might not see changes in what is going on the upper part, but let's assume for a second that the Atlantic water is warming, which is indeed doing, so we can see that for the past 10 years or something, and all the time is in contact with this other cold water that is ages old. So it's indeed doing some modifications to that water that we don't see. Isn't that like the sweet spot that we should be carrying? That interface between those two waters? It's a little the sweet spot that AMOC will not see at the surface, and maybe we'll have some changes in that part for the machine.
Yeah, I at least agree that we should look at that. Yeah, I think so.
Yep.
Thank you, Bogi, for a wonderful presentation. I was wondering, is there any kind of seasonal cycle in the inflow and the overflow?
In the Iceland-Faroe Ridge overflow, you mean, or yeah?
Yeah.
I think we know too little about it yet to be able to say that, but the measurements we have do indicate that, especially that mooring by Detlef Quatfassel, that it perhaps is stronger during summer. For the inflow, if you take the total flow, it has a seasonal variation, but it's not strong. It's on the order of 10%, if I remember correctly. But when you look at how it's distributed from between the Icelandic branch and the Faroese branch, there is a fair degree of seasonal variation. And that means also that this recirculation over the Rosengarten also seems to have a fairly strong seasonal component.
I'm curious to follow up on what was mentioned about the Labrador component. Do you have the proportions between the Labrador and the Mediterranean, Arctic Mediterranean components?
I was asked to do a science perspectives article some 20 years ago, and I made an estimate there, mainly based on work by other people, of 1 to 3. So Labrador contribution would be 1/4, and our contribution 3/4. A recent paper by Lucir et al. Says 1 to 7. Whether that means that in the meantime the Labrador Sea has weakened even more, or things are just not too accurate, I don't know.
Thank you. It was a really interesting presentation. My question would be like, what's the next big question you would like to tackle here?
I mean, this work that we have been working on together with Solveig wasn't really finished, so we'll be hopefully continuing that, and I hope there to continue our cooperation. We have just got a PhD project funded partly by Faroes, partly by Denmark in cooperation with the DMI. And we hope to continue that work. So.
Maybe the last question, Jonas.
Thank you, Bogi. If I remember correctly, thank you for an excellent presentation. I've seen similar, the current coming from, Iceland towards the Faroese, I think Kai Lokuman described it as a South Icelandic current. But regardless, of this and that, his work, but this, how, just thinking in general, how much do you think the connection is, for example, between South Icelandic, ecosystems in southeast of Iceland, for example, flow of larvae and some other fishes from the southeastern part of Iceland to the Faroese? How consistent do you think that is, and are we looking at that?
That is a question that my pelagic fish colleagues ask me every second month or so about different species. I don't know, simply. The problem is that it has to cross the ridge, and then will be from water flowing from the Icelandic region will be on the outside of the Atlantic flow passing north of the Faroes. It will be sort of on the Arctic side. We'll have a lot of Atlantic water in between. That doesn't mean that it can't. I mean, there are so many mesoscale activities that could transport it and will transport it, but I don't think I can't give you a quantitative answer to that, at least.
Okay, thank you very much, Bogi. Even though you might be retired, I hope you will never get tired. Thank you very much.